Welcome to this comprehensive guide on the state machine game design pattern, a fundamental concept for creating robust and organized game logic. The state machine pattern is a behavioral design pattern crucial in game development for managing an object's behavior based on its internal state. It allows an object to dynamically alter its behavior when its internal state changes, providing a structured way to handle complex interactions. Also known as a finite state machine, or FSM. It's a mathematical model describing a system through a set of states, transitions, and actions. Key concepts include states, which are distinct behaviors like idle or attacking for a game character. Transitions define the rules for moving between these states, triggered by specific conditions or events within the game. The state machine itself manages the current state of an object and orchestrates these transitions. Finally, the context refers to the object whose behavior is determined by the state machine, such as a player character or an enemy NPC. One of the primary benefits is organization, as state machines break down complex behaviors into manageable, distinct states. This approach significantly improves code readability and maintainability, making it easier for developers to understand and work with. They also promote modularity and extensibility, allowing you to add, modify, or remove behaviors without affecting the entire system. Debugging becomes more straightforward because individual states and transitions can be isolated and tested independently. The pattern simplifies code by providing clear delineation for which chunk of code is running at any given moment. This leads to greater flexibility and reusability, making it easier to understand, maintain, and add new features to your game. Crucially, state machines help avoid spaghetti code by eliminating large, unwieldy if-else blocks that can quickly become unmanageable. Now, let's explore the implementation process, starting with defining states. Each state is typically represented by a separate class or script, inheriting from a common base state class. This base class often defines methods for entering a state, updating its logic, and exiting the state. Next, we focus on creating a state machine class, which acts as the central orchestrator. This class holds a reference to the current active state and provides methods for initializing the state machine and changing states. Handling transitions is crucial. These are triggered by specific conditions or events within your game. The state machine continuously checks for these conditions and transitions to the appropriate new state when they are met. In Unity, state machines are commonly implemented using C# scripts attached to game objects. Unity's animator component itself is a powerful visual state machine, perfect for controlling character animations. Let's consider a common example, character control in a game. A character can have multiple states such as idle, walking, jumping, and attacking, each with unique behaviors. For instance, in the idle state, the character might only be able to walk or jump based on player input. However, when it enters the attacking state, it performs a specific attack animation and can damage enemies. Each state dictates what animation plays, what actions are performable, and how to respond to inputs. Now, let's dive into a practical C# and Unity implementation. First, we define an interface for our states, which includes methods like enter, update, and exit. Next, we implement concrete classes for each specific state, such as player idle state or player walking state, all implementing our iState interface. Each concrete state will contain the logic specific to that particular behavior. Then, we create the player state machine class, which will manage the current state and handle all state transitions. This class will be responsible for calling the enter, update, and exit methods on the active state. Finally, we define the logic for transitioning between states based on game events or conditions. For example, if the player presses the jump button while in the idle state, the state machine transitions to the jump state. While powerful, state machines can introduce complexity if there are too many states and intricate transitions. This can make them harder to manage and debug, potentially leading to bugs in the system. They might also be overkill for simple cases, where a straightforward if-else statement would suffice. Furthermore, implementing state machines can lead to a significant number of classes, increasing project overhead. However, for complex behaviors, the benefits often outweigh these potential drawbacks. If a state machine isn't the right fit, Consider behavior trees as an alternative. Behavior trees use hierarchical structures to simplify complex decision-making, often seen in AI. Another powerful alternative is goal-oriented action planning, or GOAP. GOAP is a planning algorithm that determines the best sequence of actions to achieve a specific goal. To maximize the effectiveness of state machines, follow these tips and best practices. First, keep states focused. Each state should be responsible for one specific behavior or condition. Second, define clear transitions. Ensure transitions between states are well defined and based on specific events or conditions. Third, use inheritance. Use inheritance to share common behavior between states. Finally, consider entry and exit actions to perform setup and cleanup when entering and exiting states. State machines have numerous real-world examples in game development. They are widely used for AI behavior, controlling the actions of non-player characters or NPCs. Animation control is another prime application, managing character animations based on the game's current state. UI management benefits greatly, controlling which user interface elements are displayed based on the game state. They are also essential for implementing different game modes, such as menu, playing, or pause states. By leveraging the state machine pattern, game developers can create more organized, maintainable, and extensible code. This pattern is invaluable for managing complex behaviors in their games, leading to more robust and enjoyable experiences. Remember to weigh the pros and cons and consider alternative approaches to determine the best solution for your specific game development challenges. Thank you for joining us in exploring the state machine game design pattern. We hope this guide helps you in your game development journey.